it could cope with outliers, like if some points were occluded or if some points were noisy, uh, those can be those can be handled. Not lot of noise. If the noise was, if the points were randomly distributed, then it would not be able to detect. But if the points was within some Gaussian distribution, then we saw some examples where our transform was able to fit a good line or any model for say, and it could also detect multiple instances of, so if there were multiple lines, it was able to detect all of them in a single pass. So we basically generated a half accumulator array. So from using the edge points, we voted in the half accumulator array. So what was the principle of voting? What was the basic principle of voting which half transform used? So we saw that a point in the image space corresponded to a line in the half space. And so for every edge point in the image space, we voted for multiple different lines in the half space. The line which got the maximum vote means came from the maximum edge points. The maximum edge points which, if those edge points actually lied on a line, on a single line, then all of those edge points will consistently vote for one single line, or at least multiple specific lines, not random lines. And whereas those were outliers or those were other things, they would vote for some random lines. So the actual line which was there, actually the best fit, the actual good line which would fit on those edge points would get the maximum vote. So that was the basic idea of voting method, that the voting principle that was underlying the Huff transform method. But the problem with Huff transform was that we needed to basically generate an accumulator array. So for a single line, we just needed a two-dimensional matrix, a 2D matrix. For circle, we needed actually a three-dimensional space, A, B, and the radius R, and so on. So the problem was the complexity of this half space, and then the search within that half space will increase exponentially with the number of model parameters. So as the model parameters increased, the voting procedure will become more and more difficult. Not only the memory requirement, but the problem is now to search within those half space, the bins which are peak values will get little problematic. And even some noise, some non-target shapes which may not be a, for example, line, but just almost approximating to a line, they can also produce some spurious peaks. So finding a distinct peak was bit difficult, in the sense we have to adjust the parameters. So for example, we had to adjust the bin size. If you go for too fine a bin, there was some problem. If we make our bins too coarse, it was a problem. So we had to adjust the good grid size in order to find the good peaks. So these were some problems with the half transform. So just to review again, I brought the initial slides again back here just to. So the method that we are going to discuss is RANSAC, and it is specifically mentioned for this, specifically used for these kind of problems where we detect features. For example, in the case of when we want to align images to fit a panorama or whatever, and then we compute the matching between features in one image and the other image, and now there will be some outliers, some wrong matches, and there will be some good matches. So what in RANSAC, what we'll see, we do some kind of this thing. We will repeatedly do something what is called, so we'll basically loop. We'll basically pick some random points, whatever, how many random points that we want. So for affine transformation, so if an image has been scaled, rotated, or skewed little bit, then the number of parameters in our affine transformation matrix will be 6. So if we take 3 points, we'll get 6 equations from x and y. So 3 points are sufficient to solve our affine transformation matrix. So we can just pick randomly 3 points, 3 pairs of point, and using that solve our transformation matrix, the parameters in the transformation matrix, and that will give us the way to align this image with this image. but now, is that the right transformation matrix? That we don't know, because we have randomly picked 3 points. If one of them is an outlier, this matrix will not be the right matrix. So we don't know whether it is a right transformation matrix. So how can we assess that it is the right transformation matrix? We can try to verify it. How we can verify? We can try to see how consistent this transformation matrix is with other matches. So there will be other matches apart from these three. There will be other matches that we would have got, that our feature matching algorithm would have given. So with this transformation matrix, now we try to verify whether, so using this transformation matrix, if I modify this xy coordinate here, will I get this xy coordinate or near about this xy coordinate in this? If yes, that means this matching pair is consistent with the transformation matrix that we have obtained. So we count how many such other matches are consistent with the given transformation matrix. And if that count is sufficiently large enough, is greater than a threshold, then we are happy. Then we can assume that we can accept that this is probably the right transformation matrix. If not, then drop it, repeat the process. Pick any other arbitrary 3 random points, again solve it, and try to do. So we can go on doing it for some certain fixed number of trials and find that transformation matrix for which the maximum number of other feature matches were consistent or not. So somehow we try to find the best, iteratively we try to find the best transformation matrix in this way. So we'll see the RANSAC method that we are going to discuss is basically going to use this underlying procedure, and why it will work. We'll try to prove why this procedure will work with sufficient accuracy. So again, we'll first take the example of simple line fitting to explain the procedure, and then we'll see the other applications. So this method is proposed long back, but it has been used quite frequently in computer vision, especially in robotics. This method is quite frequently used. We'll see why. So we'll estimate parameters of model by random sampling of observers. So what is this? RANSAC stands for random sample consensus. So the name of these, the meaning of these three terms will become clear. Some idea you would have got already based on what we discussed. We'll randomly pick some samples and see whether that is consistent with, or it has a sufficient consensus with other matches or not. If it has, then probably that is going to give us the best model. So we'll try to estimate our parameters of the model by randomly sampling some points in the feature space or in the observed data. So we'll explain the main idea through the help of line itself, a line fitting. So what we discussed earlier, let us say these are some random points and there is a one outlier. So if we use our least square error fitting, then we got this kind of a line. This was the best fit line, but it was not the correct line. The correct line would be this one, because the maximum the maximum points which are actually lying on this is this one, and this is actually an outlier which should not be considered while model fitting. But we don't know a priori which is the outlier, which is not the outlier. So if we just use a least square fitting, we got this one. If you have used a robust estimator function, we would have tried to get rid of these things, but again there was problem that we saw. We had to choose the scale just right to get rid of that. Or if you have taken hough transform method, that would have also given us this line. It would have got rid of this outlier. So how RANSAC will deal with this? We'll see this. Again, this RANSAC also works on the principle of voting. So what it says that if we knew, for example, if we knew this is an outlier a priori and these are the lines which are actually lying on the line, then it was very easy to fit line. We could have just got rid of this and just applied least square fitting on this line and got the best fit line. But a priori we don't know which are the outliers and which are the inliers. Opposite of outliers, inliers. Inliers are the actual points which are lying on the model. Okay. So but what we can do, if let us say if we had a proposed line, so let us say if this was our proposed model or proposed line, then from this line we can know that this is an outlier, this is not actually a point which is lying on the line, whereas all these lines, all these points are inliers to that line, isn't it? If we let us say we propose this was a line which is the best fit line, then use from this line we can know, okay, the points which are within a certain distance from this line, these are all actually inliers to this line, and the point which are away from the, further away from that line, those are outliers. So so what random sample consensus says that we randomly pick some points by which we can define our model, or which can, in this case for example, we can define our line, then see how many are inliers to that line and how many are outliers to that line, and then repeat this randomly doing this thing until you find a good enough line. Good enough line means line which has the maximum inliers, which has the maximum confidence. So that was the idea that we were talking earlier also. But in the beginning you may say this is little doesn't sound very promising, that you are randomly picking some points and repeating the trial a number of times, and you are saying that you will definitely get a best fit line. Does it really sounds promising or justifying? It may, and the other problem that may come, it may not be efficiently, because you may have to keep on doing this infinitely. Let us say a very large number of times you may have to go on keeping doing this trial for a very large number of times, then it will not be an efficient one. So what we'll see that this method indeed works. It can be probabilistically proved that for a given number of trials, this method will actually end up giving the best model with a sufficiently high probability, and that we are going to prove it. There is a mathematics, the derivation can be done. So they basically proved in the paper in 1981 that this method copes with a large proportion of outliers with a reasonable amount of trials and with a sufficiently high probability. So the algorithm basically, just to review, algorithm remains the same. What we have just discussed, will randomly sample the number of points required to fit the model. So if you are fitting a line, how many points do you need to fit a line? 2 points. So out of these points, we'll just take 2 points. Let us say we randomly pick these 2 green points. We fit a line. So we'll, in the second stage, we'll basically fit the model. Then we'll give us confidence score to that model by counting the fraction of inliers within a threshold of that model. So in this case, for example, we can fix a distance from that line. So within that distance, how many points which are lying within that, we'll count all of them as an inliers to that line, or that will be the score for this model. In this case, 1 2 3 4 5 6 will be the score for this model, and the remaining will be the number of outliers. And we are going to repeat this till we get the one model which will have the sufficient score or sufficient confidence. So in the next case, let us say we choose this point, we got this line, and probably in this case this time we got number of inliers as 14, which is a higher number than the previous case. We got only 6, and probably if we repeat this for many times, maybe this is the maximum score that we get. So we will end up choosing this line as the best fit line. So the first thing that it needs, the RANSAC model needs, for a given model that we are trying to fit, it has the first parameter that we need is the minimal set. How many minimal set of points that we need to pick from our data points. So in case of line, we need to pick 2 points only. If we are trying to do image transformation, matching one image with other image, so if the image has only been translated, for example, if there was only translation, then we just need how many points of features from one image to another page? We just need one pair of points, because the image was just translated either in x or y direction. We just get one corresponding points and subtract the x1 x2 and y1 y2, we'll get the delta x and delta y. If the image has been transformed in an affine transformation means scaling rotation in all this, then we need at least 3 pairs of points to pick up. And for more complex transformations, we have not discussed when we discussed. So right now you don't need to worry about that, but for those we need at least 4 or 8 points. So for different types of model fitting, we need different number of minimal set points. So this is what we already told. I'm so just repeating it here. So we'll randomly select S points. S is the minimal set points to form our sample. Using that sample, we'll generate our model. We'll count the number of inliers. That will be the score. That the points which are within the error bounds within a particular distance threshold of the model. And if that count is greater than a sufficiently high threshold, then we can just stop doing it. We can say that this is a good model, or we can go on repeating it for n number of trials and then find the one which gives the maximum score. So this is a general RANSAC algorithm for any general problem of model fitting in the presence of outliers. But the problem is now we need to define what is our as we know how to find out how to fix the distance threshold, how to get the number of trials. So as we have already talked about, that is fixed. We don't have to choose it. That depends on the problem, the model that we are trying to fit. How to find the distance threshold? So that depends on the assumption that we are making. So for example, if you are fitting a line and we assume that the noise, the perturbations in the pixels is affected by some by some Gaussian noise. So our image points will be disturbed by some Gaussian noise, some normal distribution with certain sigma. So our points which are supposed to lie on this line, they may get disturbed little bit here and there. We'll assume it normally, most of the time we assume it's a normal distribution. It's a Gaussian distribution is the easiest model. So we can choose this threshold. So let us say we want to have that. So now actually through this Gaussian model, we can actually decide what is this t value that we should choose, the distance threshold. So let us say we want at least 90% of our 95% of our points should lie with a high probability. So we can basically use our Gaussian equation and put the value there to get the distance threshold t. So normally it will be a function of it will be some function of our sigma. It will be some k times sigma. So for example, if we take 3 sigma, generally within 3 sigma almost most majority of our distribution falls within 3 sigma. So majority of our points on the Gaussian curve, they fall within 3 sigma from the mean. So normally the one which we choose is in fact is square root of 3.8 sigma, the distance threshold that we choose. So that says that choose t, so probability for inliers is high. So that is 95% of our points are inliers. So for that we can choose our distance threshold as a square root of how this value 3.84 comes. You basically that use the Gaussian equation curve, and from that we get this value 3. But the other things which are of importance is like how to select our number of samples that we should do, how many trials that we should do, the number of trials that we should do. So we have to choose the number of trials so that we can say that with a certain probability p, and that probability p would like to be a very high probability, let us say a 99% probability, that we will try to choose this n such that with 95% confidence we can say that we will get at least one model which will be free from outliers. And this, the value of n will be determined based on the outlier ratio. What is outlier ratio? The ratio of inliers versus outliers, E. So we can calculate this value n using this outlier ratio E. So how do we calculate n? So little bit we have to do some probability combinatorial here. So to calculate n, we will use the minimal set point as the number of points that we need to fit our model, and we need to define our probability of success. Normally, to be on a better safer side, we'll choose this p value very high, 99.9%. let us say we can choose this p. We just have to guess it, whatever you want to choose. You can choose it 98%, 99%, or whatever. And we need the ratio of the outliers. So we'll call it E, which is the proportion of outliers. So inliers will be 1 minus E. So because this is the probability, is the ratio, so 1 minus E will be the inliers. But we don't know E. If you already knew which is the inlier, which is the outlier, our problem was already solved. Our problem was already solved. So actually we don't know how which are outlier, which are inliers. So we'll keep that suspense how to deal with that little just after 4 or 5 slides we'll talk about this. But let us assume we know E, or we have some oracle came and told us what is he just did not tell the exact solution, but he just gave a hint that this is the ratio of outliers or inliers to you. Then we'll see that we can calculate n. How? So so let us do some combinatorial mathematics here. So uh, what is the probability that we pick a sample set with all inliers? So what we want to write a probability. So out of given sample points, we'll pick a sample set. Sample set means we have to pick s points. So what is the probability that we can pick s points such that all of them are inliers? So what I've said, the probability that there is the probability of inliers, or the ratio of inliers, is 1 minus E, and we have to choose s times. So here we are making an assumption that when we are picking up one, so the number of the ratio doesn't got changed by that, because we are assuming that normally with the number of points that will be there in our feature space will be too many. It will be 100 or 200, and we'll have to just pick 2 or 3 or 4 points. So if we pick 1 point, then the ratio doesn't changes significantly. So we can assume that this ratio remains the same. So every time we pick, the probability of inliers is 1 minus E, and the probability of outliers is E, and we have to pick it s number of times. So the probability that we have picked a sample set with all of them as inliers is 1 minus E to power s. So we are picking s points from our sample space such that all of the s points that we have picked, they are all inliers, and we have said that the fraction of inliers is 1 minus E. So that means we need to, the probability that first time it is inlier is 1 minus E, the probability that second times it is an inlier is again 1 minus E multiplied. So simply we keep on multiplying s number of times, so it becomes 1 minus E to power s, isn't it? So now the probability of getting a sample set which will have at least one outlier will be 1 minus this probability. The sample set which will have at least one outlier will be 1 minus this probability, because this was the probability where we said there was no inlier, there was no outlier. So having at least one outlier, we just subtract from 1 because it's a probability thing. Now the probability that all n samples that we have, all n samples at n tries that we have done, so in all those n trials we have at least one, we have got at least one outlier, will be this to power n, because this was the probability that we said that we got we got at least one outlier. So every time we got one one outlier means we'll raise this probability by n. Now we want this probability to be very, very low. We want this value to be sure that we don't get an outlier. If we ensure that this value that we have got is a very low value, is less than a certain threshold, So this is the probability of success that we want. So the probability of failure is 1 minus p. So we want this probability that all n samples have an outlier should be even lesser than that. So that means our this 1 minus e to power s to power n should be less than 1 minus p. So p, we said p will pick as 0.99. So 1 minus 0.99 will be, let us say, 0.01, 0.001, I think. No, 0.01. So that means this value should be less than 0.01. Then the value of n will give us sufficient confidence that if we do these number of trials, we'll at least end up having one sample set which will be free from outliers. So solving this equation, we take log both sides. So we get n should be greater than log of 1 minus p divided by log of 1 minus e to power s. So what it says basically, it says now, so now we know the method to get the value of n, to choose our value of n. So let us say we choose our probability of success to be 0.99, the chance of getting a good sample to be of that we 99% sure that we want to get a good sample. Then let us calculate what will be this value of n. So if our sample set is 2 and our outlier ratio is 5%, that is we have only 5% of outliers in our sample space, then in that case the value of n that we get as, that means, so maybe let me just tell you other way. So before we solve this way, so let us say we had no outliers, everything was inlier. So how many trials we have to do to get a good sample set? Just one. And let us say all of them were outliers, then how many samples we have to do to get a good sample? We'll keep on doing it, we'll never get a sample. So in between, depending on the outlier ratio, we'll get the value of n. So if the outlier ratio is less, the number of trials will also be less. So we can, with only two sample set, picking up, if we pick only 2 times, if we do trial, we can be sure of by 99% sure that one of them will be free from outlier. Even if an outlier ratio is raised to very high value, let us say 50%, that means half of your features were garbage, half of the feature set that we detected through our feature detection algorithms, where they were all wrong. Even with that, for finding this fitting a line or a thing which requires only 2 sample sets, the number of trials that you need is only 17. So you can see here it goes from, so as you increase the number of outliers, the number of trials rises only a little bit. From 2 it becomes 3, 5, 6, 7, 11 up to 17. Maximum 17 you need to be sure that you are going to get a good sample. If you are trying to do a fine transformation, we needed a 3 sample set, 3 feature points. With 3, maximum number of trials you need to do is 35. And with our current computers and all that, doing 35 trials or 100 trials is not going to take so much time, isn't it? So it's not going to be too much problem. But we see when the sample space increases, for example, if we are trying to do a fundamental matrix estimation, then we needed 8 pairs of points. So in this direction the rise is little steep. For example, here when there are 50% outliers, we need at least 1000 trials. So n increases steeply with s, that is the number of parameters, and which was there even in half transform. When from 2 if we went to 3 parameters or 4 parameters, our search space and everything exploded. Here it did not explode so much. From 2 to 3 increase only slightly. From 3 to 4 it is increasing only slightly. From 4 to 6, 5 to 6 it is increasing slightly. Even 1000 trials, I think it's not going to be so much a problem in running on modern computers. Doing an 1000 iterations should not be that much really a bottleneck. So this is just the graph. This was just a table. This is the graph which is showing for some intermediate sample point 4, and as we increase the percentage of outlier, so until, as we said, till the outliers is, let us say, 0.5, the number of tries are very reasonable. Only if it becomes greater than 50%, if greater than 50%, then probably your detection algorithm was itself a garbage. So at least we can expect our previous algorithms to give a number of outliers which is less than 50%. So within that, the number of tries that you have to do is going to be reasonably small value. It's not going to be very high value. Another thing to be noted here in this equation is that our number of tries is only a function of P, S and E, the number of fraction of outliers, the number of sample points, and the degree of success that you want. It is not a function of number of your feature points or your edge points or whatever that you are trying to fit. So it is independent of your, that means, for example, half transform, you have to run the loop n number of times. If you have n edge points, you have to run the loop n times to fit thing. Here you don't have to do even that. It is independent of the number of points that on which you are trying to fit the model. So let us see some pictorially the result of how this RANSAC does in action, in practical action. So this is an example where the image has been, I think, just translated. So these are two image points with only a translation effect, and there are some corresponding points that have been detected. So this point matches with this, let us say this point matches with this point matches with this, and so on. So out of these, we know, looking at this picture, we know that this is probably this and this. So 1 2 3 4 5, these four are probably consistent, whereas this one is a wrong match. This one getting matched with somewhere here, and this one getting matched somewhere here. It's a wrong match, because this is the beginning of the building and this is somewhere in the middle or the end. So these two matches are wrong matches. These are outliers, and others are probably inliers. But we don't know which is an inlier. A computer does not know inlier. So how RANSAC will deal with this? So because this is a translation, we just need 1 point. So as I said, these red ones are bad matches and the yellow ones are the good matches. So RANSAC will randomly select one match. So let us say it selected this match, and then with this it will try to get the translation vector and see which one are the inliers, which one justifies that. So with this one, you will get as 1 2 3 4 5 as inliers and 2 as outliers. If it randomly picked this one, then with this it will get 2 inliers and 5 outliers. So again, the voting principle is being matched here. So the thing is that if you are picking an outlier and estimating a model with an outlier, it is very less likely that you will get a high consensus score with other randoms, because outliers are all random points. So one outlier giving a consensus with to another outlier is going to be very less likely. So for example, in this case, these two outliers, they are almost consistent, but still it will be only 2, whereas the number of inliers are 5. So the confidence score in the other case will be higher than this. So what you can do, basically, this you can run this many times. So you will get the maximum score as 5. Now in this case, for example, more than one model will get the maximum score as 5. So either you have to pick this or this or this or whatever you have to put. With all of them, you would have got the same confidence score as 5, because all of them would have given the same number of inliers. So in that case, if there is no unique distinct model which gives the maximum score, you can do an averaging. because because everyone, so you take the translation from this, you find the translation vector from this, you find the translation from this, and then do an averaging. So averaging can further minimize the effect of noise. So for our feature, our image alignment or homography things, we will basically select 4 feature points, compute the transformation matrix, we'll find the inliers. So how we'll find the inliers in this case? We'll basically use our transformation matrix for a given point, apply that, we'll get the transformed point, and we'll try to find the patch around that the matched point and the original point, whether those patches are matching to a within a certain threshold error. If they are matching, then that is an inlier, and we'll keep the largest set of inliers, and we'll keep this loop until we get the best one. And if we get many things, then we can do a least square fitting on that, some kind of an averaging of estimation. So that so the coming back to the question that I raised, to decide the value of n, we needed the ratio, outlier ratio, and a priori we don't know the outlier ratio or the inlier ratio, whatever you want to call it. So what should we do then? So we can assume with a worst case, we can start with a worst case. We can assume that the outlier ratio is 50% of your feature points are garbage. So you calculate the value of n using ES 0.5. So you initialize your algorithm with that value, and then if you found that actually while running the trials, you found that the scenario was much better, not this, then you can update this value of n. So example, so for example, after first trial, if you found that 80% of them were inliers, so once you found a model, with that model you found that 80% of the points are matching and only 20% are outliers, then you know that the estimation, the initialization that you did, 50% was too large. You can improve it. So from 50% you can go to 80%. Then you can select ES.2 and then update the n value accordingly with repeated trial. So what it says, you can start with n as high as infinity, or e as high as 1, or maybe you don't need to go there. You can just start with ES 0.5, and probably this will give 100 or 1000 value. Then start running the algorithm. Now while you are running the algorithm, you fit a model, find the number of inliers. Now you get an idea of how many inliers are there. With that inlier, if you find that the new inlier ratio that you got is lesser than the initial estimate that you assume, then you recalculate the value of n, update the value of n, and keep on doing this till you have exhausted the maximum number of trials, or you have got the good model which has sufficiently high confidence score. So iteratively you can update. So it's not a problem that if you don't know a priori, because in the first and second try itself you will get some idea about the inlier ratio, and with that you will get a better estimate of n, and you don't have to go that infinite number of times. You will have to do some finite number of trials. So as I said, this has RANSAC has many applications. It is used for computing homography and other image transforms, estimating fundamental matrix. So if you have images taken from two different camera, stereo vision and other things, then in that case you need fundamental matrix to find out the matching points, to estimate depth and so on. It is also used for object matching recognition and so on. Especially in robotics it is used. We'll see some more examples just and then wind up. So this is an example from the SIFT paper itself. So these are the SIFT features which are detected. So this was the test image, and this was image in the database. So they were trying to match this book. This is not a book, I think this a packet of some cookies. So they're trying to find this in this image. So basically they did feature detection and feature matching. So some of them you can see these are inliers, but some of these are outliers. Okay, so with RANSAC they basically ended up tolerating those outliers and getting up the right object. This for fundamental matrix, the two images with different viewpoint and scale or whatever. So these are Harris features which are detected. With RANSAC, if you apply the RANSAC, you find that out of total 190 features matches, it was able to separate out 99 matches which were inliers. So you can see all of them are getting aligned somewhat in the same direction, and these are all outliers which are randomly getting matched. These are 89 outliers. So these are some results from some paper or some. I just took those slides from internet. Um, this another thing that you can do with RANSAC. For example, in this case, this is a 3D point cloud which is being showed. So some depth sensors, they generate this kind of a 3D point cloud. So what it basically is showing that there is a table and there are some objects kept on the table. So it is especially used for robotic vision. So if a robot arm has to go and pick up an object, how does it know where is the object and all that? So first of all, it needs to separate out the objects from the background, from the table at least. So how did this table thing got removed in this image? For example, if they actually use the RANSAC to do that, how basically, because this table is a plane has a equation. You can fit a model to the plane equation, and you can estimate their parameters. You can randomly choose points and do random trials, and by that you can find a good fit which actually fitting on the plane, and then with that you can get rid of the plane and can only get segment out the actual objects. So there are more details to it, but I'm just telling you that RANSAC can be used for plane fitting and all those things. For we'll still come to that problem, that number of multiple models, whether it can fill or not. So what are the good things about RANSAC? The method is very simple, algorithm is very simple and general. It can be applied for many different model fittings, and often it has been found to work good. It is robust to large number of outliers, as large as 50%, applicable for larger number of parameters than half transform. In half transform, if you had only 3 or 4 parameters, our space will become unmanageable. Here we can go up to 8 or more than that without increasing the complexity too much. And the parameters are easier to choose here. In the half transform, you have to do a lot of fine tuning to find out the bin size and all that. Here the parameters are relatively easy. They are more intuitive to choose. The number of trials, the distance threshold, and the sample set. These are very intuitively selected parameters, so it's not a problem finding the parameters. What is not so good or disadvantage of RANSAC? Again, this is the time may grow up with the number of model parameters, so you may have to do lot of trials if the parameters are large. It is not as good for getting multiple fits, so it, or there may be some more intelligent way to do that multiple fitting, but it is not as good, so that is a disadvantage. This is not so good, whereas half transform, it was advantage there. You could actually fit multiple models in just a single pass. And of course, if it is a general template like a car, a model of a car and all that, half transform has a general half transform which we didn't discuss just to avoid the details, but RANSAC cannot do that. RANSAC can only do good for not for approximate models. So these are some disadvantages.